So let's look at what happens in a no solution, also called inconsistent, and infinitely many solutions, called dependent, cases with matrices. So this first matrix, if you take a look at it, it's already been written out as close as it can to row echelon form. Diagonal ones weren't quite possible. We couldn't just get a 1 down here in this last corner because that last row has all zeros except for the very last number. So sometimes when you work a matrix out, you get to this point here with row operations. And if we write this out as 3 different equations, let's see how it goes. The first row is just x equal to 3. The second one is just y equal to 5. But the last row is just a 0 from the other side is equal to negative 6. And so that tells us something about our system. When you run into a statement that is not true, like this, 0 equals negative 6, then that tells us there's no solution. So this is what a matrix would look like when there is no solution to the system. Now this last one down here, notice how the last row is all zeros. That actually works out better than the last one. So let me write it out here real quick. We have x plus z is equal to 8 and y is equal to 7 from the second equation. So what's going to happen here is that last row is just 0 equal to 0. And so there's nothing really going on here, but it is telling us that we have infinitely many solutions. Now, I mentioned this way back in section 5.1, but it's good to know now how we actually write out our solutions when there are infinitely many solutions. So what we do in these cases when there are infinitely many solutions is we take the equations that we do have and still go ahead and solve for x and y as much as we can. Even though we're not going to be able to solve for just one number for everything, we can still at least have x equals and y equals to something. Well, in this case we do have y equal to 7, so we did get a solution for y. But for x, I have x plus z is equal to 8. So what I'm going to do here is I'm going to subtract over the z and make that into x equals to 8 minus z. That's kind of a solution for x that makes it based on z itself. And then z, we don't have anything for z. Z can be any number that we choose. So in this case, we write all solutions, and we always write our solution with x, comma, y, comma, z. So in this case, our x would be 8 minus z, our y is 7, and our z is still just z. And so that's how we can see the solutions, even though there are infinitely many of them. That's the way they would look like if we were to solve it. So just as an example, you can choose any number for z. We could choose z equal to 1, and then we'd have 8 minus 1, 7, and 1, or 7, 7, 1. So we can choose lots of different numbers for z and get lots of different solutions for x, for y, and for z. For instance, if z is 2, 8 minus 2, 7, 2, 5, 7, 2. And so this is what each solution would look like as we produce different solutions for the infinitely many that we have.